Possiamo andare? Vado? Good morning. Good morning, ladies and gentlemen. Welcome to the RCMS webinar. As you see, I'm here with the RCMS consortium, a lot of people. Very happy to be here and to share with you some content and results of our RCMS Horizon 2020 project. Thanks for coming to this webinar. Before starting, just a few words about how to do this webinar. We are going to have a very short introduction by myself about the project, and then three presentations from the team. We have Anand Lepek from IAI, Niels Kemme from APC, and Norbert Petz from Cellor. It is supposed to be something like 40-45 minutes in order to be focused and very well defined. If you want to interact with us, you have in your control panel, you have a place in which you could text your questions or your comment, whatever. We are going to do like this. I'm going to check the questions after the end or during the different presentations, and I'm going to check the questions at the end. And after each of them, if there are questions, I will ask my colleagues to reply to those questions. So thanks to the consortium. You can sit down now, and I can start to introduce the project. Kruchi, you can when I give you the instruction, please go with the video. So first of all, welcome again. The project we are talking about is called RCMS, Rethinking Container Management System. It is about a new concept of yard container management in terminals, where terminals can be, in principle, port terminals, but it can be applied also to other kind of terminals. The project is sponsored and co-funded by the European Commission under the Horizon 2020 program. It is a project lasting 21 months. We are close to the end, so we are already able to present some results. The overall idea of the project is to compare this new concept of yard management, comparing to, let's say, more traditional technologies, and to simulate in different ways, and specifically in two ports, in two terminals, in Gdansk and in Koper, where we are by chance here in Slovenia, to compare with traditional technology and to see which kind of benefits this concept may bring to the market, and obviously also to check the potential return on investment for private investors like private terminal operators, and also in a global perspective, such economic impacts at the global port level. And finally, also to measure the impacts in terms of the transport network, both at macro level around the port and at macro level on the transport network itself. I think that the best way to start with is to show you a very short video, because this is a video in which you can really understand in a few minutes what we are talking about. Then I will give the floor to my colleagues for the three specific presentations. So please go. Okay, back again. The video is really self-explanatory in terms of the concept, but behind this concept there are a number of very, let's say, deep technical details to be explained. This is the topic and the focus of the first presentation from Anand Peck, Israeli aerospace industry, that is going to explain you more in detail the operational concept first, and also some technical brief about, for instance, the main element of the project in terms of robotics, meaning the AGV, but also some benefits in terms of automated storage solutions. So, Anand, the floor is yours for, let's say, 10 minutes.
Thank you. Thank you for joining us. So we'll start with general overall look on the project, and then we'll dive into more technical details and operational concept. So the RCMS is an infrastructure for vertical storage of containers with a major benefit of having better space utilization, being able to store containers one on top of the other for 10, 15 floors were the numbers that we use during this project, and of course in other places in the world it can be even higher. The project, from the top view, you can see the general layout, which we will dive into more details later on. We differentiate between the sea side on the left here and the land side on the right here, and in the middle there is the storage. So we have three main elements. We'll now dive into more details into each one of them: the interface with the sea, the storage inside the infrastructure, and the interface with the land side. This sketch is already after some design by our partner Selhorn, which will get into more details during his presentation. So the first part, the interface with the sea side. The interface with the sea side.
I'm trying to.
That's where we release the twin slopes before we put the containers on the balconies, which are outreaching from the building. And we have a few balconies, you can see here. And the AGV, which was designed during the project by II, is a unique AGV with the omnidirectional capability. And the AGVs being controlled by central software which manages all of the resources in the building, is getting its missions and knows exactly to which balcony to drive and under which STS crane to wait. Under the crane, we have a circular queue in order to maintain the right order when we are uploading containers into the ship. And when we are downloading containers, it doesn't really matter which AGV is arriving first. And now we'll get into more details about the AGV later on as part of the discussion of the storage. This is the next element. The storage provides, we'll see some key performance from HPC later on, but in general, we are able to have many more containers per hectare than any other current technology. We can, as I said before, we can have storage 10 floors high, 12, 15. It's very site dependent and according to the requirements of the specific terminal. Inside the storage, this is the top view of a typical floor. What we have here is streets driving from side to side in parallel to the quay, and avenues driving perpendicular to the quay between the land side, between the sea side and the land side. Driving direction, storage cells. Those are the storage cells. We have elevators and AGVs. So the streets and avenues, we have in each avenue and each street, for robustness, we have a single direction in which any of the AGVs can drive. This makes it very robust operational, and the number of the avenues, how many free lanes we have, is an output of the simulation which was running by HPC. And that dictates the number of the density of the entire building. The storage cell is very unique. This is the storage cell. In each storage cell, we can store either 2 20 feet or a single 40 feet. The containers are being stored like floating in the air, enabling the unique AGV to get under the container and fetch the container in one step. This enables us actually having zero shuffling, because while we are driving in the street, then by a single move, we get into the cell and fetch a container. So this is actually a zero shuffling. And the next item is the AGVs. Those are 2 AGVs being coupled together. It looks like that. We have a coupling mechanism, and it doesn't matter from which direction the other AGV is arriving. It can be coupled from either direction of from any side of the AGV. The AGV has a lifting platform, and on top of the lifting platform, the container is being dropped under the STS crane or being picked while taking it from the cell. We have a very good design which enables us to work 8 hours continuously with only 2 hours of charging. It is completely electric vehicle. It is smaller than a container, and using the special Omni wheels, we can drive in any direction, which is very important in order to enable us to work in the specific layout that you saw before, that there is zero radius for maneuverability. Unlike with today vehicles. How it works: this is the AGV inside the cell. Currently, the lifting platform is in the lower position, and then it is being lowered upwards, as you see here. While it's getting being upright, it is actually taking the container, and then the AGV can get out of the cell and drive to the STS or to the waiting trucks on the bottom floor. Comparing with today's traditional AGVs, then our AGV is much more compact. Of course, lower cost because of that, lighter in weight. Also, for the horizontal transport, it has its benefits because of the zero maneuverability. Then we can have the horizontal transport much shorter distance. The width is much smaller than today's horizontal transport areas where we are using AGVs. It's electric, and we can either take a single 20 feet or 2 40 feet, and that's also another benefit during the operation. While unlike these huge AGVs currently carrying a single AGV, so we are wasting a lot of energy. So here with our AGV, we are much more efficient because we carry 20 feet with a single AGV, and we don't waste resources. We have numerous elevators being spread around the building. The number of AGVs, the number of the elevators, the locations of the elevators is a result of the optimization and simulation run by HPC with the algorithms provided by IAI. A single elevator can carry up to 70 tons. It's based on cables, and it moves in around about 1 meter per second. That's pretty fast. This is already a kind of design of the elevator. Now the third part is the interface with the land side, in which we move the containers to and from the trucks coming from the land. What you see here is a top view of the interface. We have multiple slots. It's also, you can see here, side view. Those are the slots. This is the crane. We have a number of cranes. And the simulation optimized the working and where each of the OHBC overhead bridge crane is working. And the AGV is getting out of the building, going to the right place, the AGV, the truck went to the right place, to the right slot, and the OHBC is taking the container from or to the truck and to from the AGV, and then the AGV continue with its mission to storing the container inside the building, using the elevators to go in the floors. So what we saw here in brief is a top view, some brief about the operational concept of the RCMS, discussion on the three main areas: the interface with the seaside, the storage with the unique AGVs that we developed, and it's very unique during the project, and the interface with the land side. The project provides space utilization much better than any current technology. It is modular, meaning that you can build the building in steps. You don't need to build the entire infrastructure along the entire quay from day one, and it's very robust for any potential errors. And right now, Israel Aerospace Industry is looking for places and partners in which we can start working on a pilot. So I would like to thank you for joining this session, and questions now or later.
Actually, we don't have any questions, but they may come. So thanks Anand for the presentation for the time. So now the floor is for Niels. Niels came from VPG, Hamburg for Consulting. The presentation from Niels will be about one of the main aims of the project I was mentioning before, is comparing and assessing the performances of RCMS with other state-of-the-art technologies in handling containers in terminals. So, Niels, the floor is yours.
Thank you, Alexio, for the introduction. As you said before, so following the technological introduction of the system, presenting the functionality and the basic concept of the RCMS, I would like to address the question, first of all, if the RCMS system as planned is actually feasible, and if it is able to achieve a better performance than existing systems. So the question is, as it said here, is it a new benchmark for efficient terminal operations? Then, in principle, the RCMS, as it has been presented by Hanan, sounds like a very interesting solution. It offers improved stacking density and area utilization, as has been highlighted by him. It does not require any unproductive container rehandling, which means shuttle moves or housekeeping moves, which are usually required whenever you stack the containers. It also enables full automation of the system, and it shall enable competitive productivity and service levels for landside and waterside operations. And it will also, or shall also, reduce emissions, not just exhaust emissions, as it has been mentioned by Hanan before, but also light and noise emissions, as the operations mostly take place within a building. And at the same time, it shall improve work safety. But the question is, which we will address here in this presentation, does it actually work as it has been planned before? Which productivity levels can which area savings can we and how much additional throughput maybe area savings, and ultimately also how much equipment is required in order to achieve these gains in storage density. So ultimately the question is the RCMS better than state-of-the-art systems? Which brings me directly to two important questions. First of all, the question is, what does a better system mean? So there are several ways to assess container terminal and container handling technology. You can evaluate them on several criteria and several dimensions. Noteworthy are, of course, costs, investment costs, operating costs, and also environmental considerations like noise, exhaust emissions, etc. But most important of all, which is the baseline for any system, is the operational performance. And also for the operational performance, there are several different criteria which have to be taken into account. from our experience at HPC, I think it's most noteworthy are the service level and the storage density. So, meaning the service level is the productivity which can be realized at the water side when working on the vessel, and at the land side when serving trucks and trains. And storage density obviously refers to the throughput that can be achieved per area on the terminal. The other question is, what are the competitor systems with which we have to compete, which we have to outperform in some aspects? For me, the state-of-the-art systems are, on the one hand, of course, the conventional RTG TTU system, meaning fully manual rubber-tired gantry cranes, which is the most common system, most popular system on relevantly sized terminals all around the world. And the other state-of-the-art system is the ASC AGV system, which is also meanwhile proven and in operation at several terminals also all around the world, which is fully automated. So how to assess then if the RCMS is better than these two systems? In order to make it as realistically as possible, we have not done this for some arbitrary terminals, but we've done it for two real existing case study terminals. As Alexis said before, the case studies are for the GTK terminal in Gdansk, Poland, and the other terminal in Koper, Slovenia. As you can see them here on the picture, the left one is the GTK in Poland, and the right one, that's a picture from Koper, Slovenia. The terminals differ in some aspects. The GTK in Poland is an existing facility, a very small-sized terminal, and the idea for this terminal was, since we have a given footprint, to maximize the throughput for this given footprint. On the other hand, for Koper, we were just giving, let's say, an outer planning framework. At the same time, we were given a target capacity, which has to be achieved by a system. And then the idea was to minimize the area requirement for that target capacity. Consequently, our idea was to develop alternative terminal plans, terminal designs with each of the three systems, namely a rubber-tired gantry crane, automated stacking crane, and the new RCMS solution for each of the two terminals. Here you can see our initial plans for these solutions then. In the top row you can see the solutions for Gdansk. First of all, we have the RTG, then the ASC, automated stacking crane solution, and finally the RCMS. And in the lower lane, we have the solutions for Koper, pretty much in the same order. In order to confirm and validate our initial terminal design plans, and also to get more insights about the system, particularly regarding the RCMS, where we had no experience values when we started our analysis, we did some simulation analysis. Essentially, we simulated all 6 alternatives. Here you can, for example, see a visualization of the simulation for the RCMS solution in Koper. At the water side, we see there's one larger vessel in Perth. It's currently operated by 4 gantry cranes. You can see the red and green AGVs moving around here on the 2 balconies, which serve as interface between the RCMS building and the key cranes. Red AGVs are currently empty, whereas the green ones are laden. On the rear side of the building, you see the so-called overhead bridge cranes, which are the interface between the building, or handle the interface between the building, between the RCMS, and external and internal trucks. We also see the internal trucks that are moving between the rail station on the terminal, served by rail cranes, and we see external trucks that are coming from the gate and driving directly to the RCMS where they are loaded and unloaded. We, of course, received a lot of information from the simulation. For all 6 designs that we analyzed, we were mostly interested in the results, of course, for the RCMS, because we had no experience with that kind of system, and we were really curious what kind of productivity levels can be achieved by that system. And on this slide, you can see the productivity levels and of the RCMS equipment itself, meaning the AGVs, the elevators, and the overhead bridge cranes at the land side. And in addition, we see probably the most important terminal performance indicator, the ship-to-shore crane productivity, the T crane productivity, which is shown here in the upper left. This graph shows the productivity variation, the blue line, over the course of a week. And the red line shows the average productivity that is achieved. Here you can see that we were able to achieve a target productivity of 30 moves per hour. Theoretically, we can also achieve higher productivities with the RCMS, but we were essentially targeting productivity of 30 moves for all of the systems that we compared in order to compare apples with apples in the end. But with adding more equipment, you could achieve higher productivities also with the RCMS. Additionally, you can see from that figure that there is a kind of a corridor in the performance or in the productivity at the ship-to-shore cranes, which is essentially between, let's say, 25 and 35 moves per hour, which is comparable stable when comparing to other systems, mainly to manual systems like the RTG system. For these systems, you usually see a much higher variation in the productivity that is achieved at the ship-to-shore cranes, whereas the RCMS is able to produce a very stable waterside productivity, which is usually preferred by terminals, since this creates a very plannable environment. In addition, you see here on the right the productivity of the AGVs. There is a slightly higher variation in the productivity, but the average is around 3.5, 4 moves per hour, which is, from my perspective, pretty good when considering the slow speeds that they drive. On the lower picture, you can then see the elevator productivity. Elevators are able to do some 20 productive lifts per hour, and the OHBCs are really extraordinarily productive. They are able to do some 40 loading and unloading moves per hour. So then, using this new information that we received from the simulation, we updated our initial terminal design plans and determined the final equipment requirements for all systems compared here. And it's summarized in this table. So here you can see the 3 systems that we compared: RTG, ASC, RCMS, and the different equipment that is needed, and the equipment requirements in both columns then for GTK and Koper. For example, for Koper, we would need 44 RTGs and 95 TEUs for that system. Looking at the RCMS, we can see that when looking at the 10 high RCMS building, we would need 6 elevators, 2 OHBCs, and 45 AGVs, all to achieve a target productivity at the waterside of 30 moves per hour. When increasing the stacking height to 15 high, which consequently boosts capacity in parallel, we would just need 1 additional elevator. OHBCs already provide sufficient handling capacity, and we would need some additional AGVs to handle that additional capacity. Besides these just numerical results, the simulation also confirmed or revealed some other findings which are worth mentioning here, I think. First of all, since the RCMS has never been tested before, this detailed simulation, which really simulates all the processes, all algorithms in detail, the simulation confirmed that the system is actually feasible. It's doable as planned. The processes and algorithms are already providing very promising productivities, which can achieve competitive service levels at the water side and at the land side. And it's additionally worth mentioning, considering the fact that this is a very new system, that there is still some notable improvement potential already included in the system. Worth mentioning are, for example, that we are already thinking about increasing the speed of the vehicles, which would increase productivity of the system again. And there is also some potential for improving the algorithms, which may improve the productivity of the entire system by some 25%, in addition to what we've already seen so far. Finally, looking at some KPIs, key performance indicators for the system that we compared here. First, the results for the terminal in Gdansk, the GTK terminal. As said before, here our objective was to maximize the capacity for a given footprint of the terminal. And as you can see here in the first lane, here are the productivities measured in TEU that we are able to achieve with the systems. And the RCMS, in particular the 15 high building, is able to outperforms the other systems in terms of capacity. It provides a more than 100% higher capacity than the other automated solution, the ASC system. This is also confirmed by another KPI, the storage density, measured as TEU slots per hectare. Here, the RCMS, the 15 high, produces a almost 4 times higher density than the existing ASC AGV solution. Another KPI, which is very impressive, I think, when considering salaries and personal costs, it's the annual throughput per staff, the TEU per employee. And here, the RCMS building is again able to achieve a more than 100% better level than the ASC or even the RTG solution is able to achieve. Looking at environmental considerations, also here the RCMS performs best. It reduces local exhaust emissions by almost 80% compared to the traditional RTG TTU system, which is mainly diesel powered. For Koper, the results are very much the same. It's just on another level of capacity, since the terminal is much bigger. Here again, the RCMS, here we have a 12 high RCMS. Here, this system is also again able to outperform the other systems. In this case, it provides a almost 100% higher storage density than the RTG solutions. It again provides the best ratio in terms of TEU per employee, which is again more than 100% better than the RTG solutions, the conventional solution, and it is also best with regards to exhaust emissions. So, in summary, our analysis from HPC revealed that the RCMS is feasible as it has been planned before. The control algorithms lead already to a very efficient resource utilizations, so with which we are able to achieve competitive service quality for vessels, trains, and trucks all at the same time. And most noteworthy of all is the fact that RCMS achieves unrivaled storage density. There is no system available in the market which can compete with the RCMS with regards to storage density. So consequently, when you have, looking at what field of application or for which type of terminal the RCMS is particularly suited, we could say whenever you have a terminal or a port that is, wants to boost its capacity, when you are restricted in space, and when you have limited possibility for reclamation, and when you have high labor costs, and when there is a certain fact or certain level of environmental awareness in your place, then I think there is no other solution than the RCMS. The RCMS is then the ultimate solution to boost your terminal capacity. Thank you. That's it from my side. happy to receive any questions.
Thank you very much, Niels. Very comprehensive overview with some very interesting and promising results in terms of comparison. And I have to highlight that this is a comparison that has been done with a real in-depth simulation, meaning with really checking the different algorithms, checking the state-of-the-art technology. So it's really an in-depth research that has been realized through this project. So the results are, let me say, scientifically quite valuable. In the meantime, we have received the first question that I think Anand could answer to. Is about the operational concept of the RCMS, and specifically the question coming from our participants is how the container are moved from RCMS to trucks specifically, and which kind of possibilities we have in the last, let's say, part of the game between RCMS and trucks.
Okay.
Maybe
here Niels will bring the right slide. You can put a slide where we see the OHBCs. So we have a few OHBCs, as you see now on the screen. This is top view. The OHBC has the capability to turn, to circulate the container. So we have a few OHBCs that are moving along the building on the bottom floor. And you see that also on the right picture. And the AGVs are parking in perpendicular to the truck. The OHBC takes the container from the AGV, turn it, and put it on the truck, and vice versa from the truck, turn it, put it on the AGV. It puts it on the AGV exactly like the STS operator put the container on the AGV. And as you saw, the AGV, when you saw the picture, the drawing of the AGV, it's actually from a CAD file. It's not a Photoshop, so it's coming from a very, very detailed CAD file. And then you have those guides enabling to put the container on the AGV. As per the other aspect of the energy, we'll answer that after Selhorn's. So I hope that I managed to answer this question.
I would like to add to Hanan that this is nothing new. So OHBCs are already in operation at other terminals. It's proven technology, and also rotating spreaders. That's nothing new. It's in operation at other terminals. For example, at rail terminals, there it's quite common that the container has to be rotated when unloading it from a truck and placing it on a train. So this is a very proven concept already that we are using here.
Okay, I think if you want to have more details, please ask a specific question. So we go to the last presentation. As you may imagine, building an RCMS is not the easiest part of the game, and there are specific things that has to be studied, researched, and this is exactly the aim of one of our partners in the consortium, that is Cellon, and Norbert Pett from Cellon will elaborate on how to build the RCMS from the civil work and the optimization point of view. Norbert, the floor is yours.
So, hello also from my side. I like to spend a few words to get a certain understanding of what it means from the technical side to implement the RCMS, and what do we understand as the RCMS. We have heard about the operational system now from Niels and Hanan. So now I like to give you a certain understanding what does it mean, the RCMS. So what is the RCMS key structure? This is basically a building to store the containers on a multiple floor instead of an open stackyard. So you can see on the right picture below the open yard solution from, as an example, the RNG system. And on the left picture, highlighted, for example, RCMS building as a structure. So from a top view along the quay wall, to have a better understanding, the cross section shows you basically the building itself. So what are the requirements which we have to consider for the technical planning? So the requirements came from the operational demand. This means that we have to consider the driving of HGVs inside the building on all floors, that we have the direct accessibility of the HGVs to each container, so no shuffling was required, that we have one container high at each floor, so we are not putting one container on top of each other. So we have moving HGVs in operational mode from one floor to the other. So this is where we have the elevators for. And we consider the direct delivery of containers from the STS crane onto the building, the balconies which have been introduced. So based on this, we have to consider certain requirements to the structure. So what does it mean for the structure itself? So that means that we have high traffic loads coming from the HGVs, which are carrying full containers, so which is considerable loads for such a building. We have, in addition, high loads for the accumulated containers which are stored within the building. Then we have specific requirements on the inclination and flatness from HGVs omega wheels. Also, and this is one of the main challenges, to consider the spacing between the supporting elements, whether these are columns or walls. But we need to allow that HGVs obviously can move freely with a 40-foot container and plus additional clearance to the sides. And we have considerable floor heights to allow the high cube containers plus the HGV chassis to be lifted within the building. So a few words to the technical planning of the RCMS. So at the beginning there were preliminary design discussions and issues in terms of what would be feasible in terms of structure. So, I mean, possible structures, so like a steel structure was considered, and also concrete structure. So we came to the conclusion that the concrete structure is more feasible than this poor steel structure in order to allow for the high loads. So there was an interactive and iterative process from the operational, from the technical planning side in order to come to certain layout solutions. How could this look like, the internal of the building? So we developed an initial layout with load-bearing concept of columns, as it is typical for high-rise buildings or office buildings. So what we came up with, column diameters of 1.4 meters, and considering the number of column rows we needed, so we decided that the main disadvantage of the inefficient utilization of space should be looked into another solutions. So we came up with a, let's say, more developed layout of load-bearing concept that we introduced instead of columns, load-bearing reinforced concrete walls throughout the building. So you can see on the right picture what you have seen before, this what we call storage cells, but basically the walls around are required structural elements for the building. The advantage is that we have a more efficient utilization of space within the building, and therefore reducing the overall dimension of the building in horizontal dimensions. We improve also the redundancy of bearing members, so in terms of failure or damaging to one of the bearing walls. So in total we have a more robust structure, and we have a more even distribution of loads within the building. So once having looked in the superstructure, the building itself and the live load, we needed, of course, to consider how the foundation of the building might look like. So the substructure basically means the transferring of the high loads from the building into the subsoil. This proved to be, for the specific sites, a challenging approach. So at the end, both sides of Gdansk and Koper called for special deep foundation. We opted for poured concrete piles. But it needs to be mentioned that especially the foundation, which is also a cost driving factor, depends heavily on the present subsoil conditions. So whether we have soft cohesive soils or whether we have sandy non-cohesive soils or we have even rock. Therefore, the piles which have been designed for this case studies could be either very short or even not existing at all, so depending really on the site conditions. I don't want to go into all the details because this would be a bit too long for this webinar. Nevertheless, in order to mention it at least, so then a number of technical issues which have been considered, which have been discussed also from operational needs and requirements. Just to mention a few of them. So the reefer container supply and access called for special solution in order to separate the fully automated operation within the building and the reefer connections. The elevators with a high carrying capacity of at least 70 tons needed to be included into the concrete structure. The rainwater discharge proved to have considerable flow due to the large areas which we have to the water. Firefighting concept within the building was lengthily discussed, and different solutions are possible. Also, emergency and maintenance access was also a technical issue. So how to incorporate staircases or elevators for maintenance stuff. In addition, illumination within the buildings, whether permanent or during maintenance, is required. Wi-Fi supply to the reinforced concrete structures in special consideration. Power for charging points of the HEVs is a specific issue. And also, depending on where the site is located, to keep the balconies free from ice and snowy conditions in order to allow the omniwheels of the HEVs to drive. So these are optional requirements, really depending on where the RCMS might be located. So during the process, there had been many optimizations done. In addition to this, we looked in a completely different direction, aside from a steel structure or concrete structure, to have introduced innovative materials where extensive calculations went on composite materials. We revised the roof construction to adapt them in a more cost-optimized way. Cost optimization was a main goal for all the design works, which needed to be performed based on detailed calculations in order really to have a certain level of security of the structural feasibility. So what was our final solution for this project? So we came up that the heavy-duty reinforced concrete structure is the right solution, or the most economical solution, based on board piles. This proves that the RCMS in first hand is feasible from the technical point of view. So we have developed a concept which allows flexibility in the design height and also in horizontal dimensions. We have developed models, so which we can adjust to the actually requirements on demand. So, but nevertheless, there is not this one solution which has been developed and can now be used for all the sites. It must be clear that there are many site-dependent factors are involved and lead maybe to further improvements or even slightly different solutions. So this is from my side, and I think, I'm not sure, Alexio, what questions?
Yes, we have some questions. The first one, I think it's more related to the operational concept and the comparison. And the question is if we have some, let's say, elaborations, or we discussed about specifically energy consumption. I think you are going to answer it.
Well, energy consumption, there are several drivers of energy consumption within the RCMS. It's we have on the one hand the AGVs, which are electrically powered, which have to be charged. In addition, we have the elevators, which turned out to be major driver of energy consumption within the building, since all AGVs and the containers have to be lifted between the floors, and we have the OHBCs. But I don't have the exact numbers in mind because it differs per terminal and depends on the throughput volumes. But what I can say is that the total energy consumption is pretty much the same as we currently experience for traditional ASC AGV terminals. So essentially, the AGVs have to drive between different locations. Containers have to be lifted either per crane or per elevator, and in total it sums up to a very similar level of energy requirements. If you're interested in some precise numbers, just send us an email.
Thanks a lot. The second is more for Norbert. It's about, again, the civil part of it, and about the foundations specifically. And the question is if we have specifically elaborate on the let's say the economics of the big foundations we should have to build for this RCMS concept.
I mean, I'm not quite sure what the question is in terms of economics. I mean, we looked in different solutions for the foundation. Does it refer to the RCMS itself?
Well, I think the question is about the fact that there is a huge load to be, and so the foundations, in principle, as you explained, in principle they are big. There are big number of piles. And
yeah, I mean, I mean, there's no way in this subsoil condition which we have in this case studies that we can neglect a deep foundation, so basically pile foundation. This has been considered. Comparing this with the state-of-the-art systems, we have an advantage because due to the deep foundation, so we don't have the issues with settlement due to additional loads from the container stack, for example. So, but as I said, this is really site dependent and needs to be studied in detail case by case.
And it also has to be mentioned that also ASC solutions often require deep foundations. So it's not a unique aspect of the RCMS, but also other technical solutions require deep foundations.
Next question is about, I can directly answer on that because it's a really side-by-side situation. This is about the visual impact of RCMS. Of course, this is really a site-dependent issue, and there are places in which you cannot even think 1 second to build such kind of system, because maybe they are ports or terminals right in the middle of a city, and there are a number of examples in Europe, and you can not really think to build such a high building. But nevertheless, even if you build in terms of handling and efficiently, if you build RCMS in a way that is high, not that much higher than traditional technologies, you can have already some benefits, and also traditional technologies have some visual impact. Next question is something that we are going to deeply answer in the next webinar we are going to have at the end of January together with our final conference. So the elaboration on cost in terms of investment and maintenance, that of course it is reflected into different issues. The cost for the terminal itself in terms of return on investment for an operator, and on the other side is more on the socioeconomic impacts that are going to be studied through a specific cost-benefit analysis from the port community point of view. So this is the question is going to be answered in a couple of months more in detail. And this is also an excuse for me to invite you both to the final conference and to the webinar, to the next webinar that both they are going to be organized at the end of January in 2 months. The very last question, it's up to us how to answer, because in reality we didn't study that much, is what about the different handling labor regulations, if they have been studied or not. They have not been considered right specifically, I think, but indirectly somehow in the simulation.
Well, it has been considered when we were thinking about the processes, how interchange or the interfaces are organized. Whenever we have any interaction with manual operations, like at the water side, at the key crane, or with the external trucks on the land side, or with reefer containers, for example, how they are handled. We've thought about that in very much detail and considered regulations and solutions that are currently already accepted by authorities in other places with regards to traditional automated storage concepts. So this know-how, this knowledge, this experience has been considered, but we have not looked into specific requirements for these places. You also need to understand that in both places, Koper and Gdansk, so far there is no automated container handling technology in place, so there are no specific requirements which we could have considered so far. Consequently, our analysis and our planning results are based on, let's say, international standards with regards to automatic container handling processes.
Thank you very much, Niels. Let me check. I don't see any more questions. So thanks a lot, first of all, to all the participants. It was just 1 hour, so thanks for your time. Again, I invite you to the final conference in Brussels. It will be in Brussels at the end of January, and also there will be a second webinar. The registration of the webinar will be available on the RCMS website soon. And thanks to the portal Koper that is kindly hosting us here to do this webinar, to the speakers, and also to all the consortium that is running RCMS, and hopefully see you soon in a couple of months. Bye-bye.
Thank you.
You started?
Actually, do you have a list of those who participate? Can you circulate that among us?
Yeah. They should be registered somewhere.